Okay, so here is page 3 of your notes. It's talking about light as a particle, and when light is a particle, it tends to carry what's called quantized energy. So Maxwell Planck theorized that energy was transferred into chunks known as quanta, and that just means the discrete amount of energy. And this is equal to something called h, which we'll later define in a second, times a frequency, which is always seconds to the negative 1. So h is known as Planck's constant. It's this number that never changes, just like the speed of light's value never changes. And it has units of joules and seconds. This units of joules will tell you what the energy of a wavelength or a photon possesses by giving its frequency. So this S and this S will cancel. If we don't know the frequency, we can always use the wavelength and plug it into C equals lambda times nu like we have been doing. But if we do know the frequency, we can use the equation E energy equals Planck's constant times frequency. And Planck's constant has the units of joules times seconds. Frequency is seconds to the negative 1. So when these cancel, you'll get joules, which represents energy. Again, if you don't have the frequency, but you have the wavelength, you can just use this equation we've been using to define that. And this is meters, and this is seconds to the negative 1, so this is meters per second. And remember, this is the constant 3 times 10 to the 8th, and this is a constant 6.63 times 10 to the negative 34th joules times seconds. So, there are lots of different ways you can rearrange E equals Planck's constant times nu to find different variables. You don't have to use this problem-solving chart. I thought it was a nice little tool. But if you want to use this first and then this, or you just need to use this, depending on the problem, you can go back to this chart and see which equation you can use and how it's arranged. So, let's do a practice problem. It says, what is the energy of red light if its frequency is 4.56 times 10 to the 14th hertz, or seconds to the negative 1st? So, it's asking for the energy, and energy is that E equals HV equation. So in order to use this equation, we already know this, it's a constant. We just need to know our frequency. And they give us frequency in hertz, which is the same thing as saying seconds to the negative 1 power. So energy equals Planck's constant, 6.636, or 63, times 10 to the negative 34th joules times seconds, times the frequency, 4.567 times 10 to the 14th. And I'm going to use seconds to the negative 1st instead of hertz, because that way it shows that my units will cancel. And so now, your answer is 3.03 times 10 to the negative 19th joules, because joules is the only thing left over. Okay, let's do another one. On the next page, number 2, it says ultraviolet radiation has a frequency of 6.8 times 10 to the 15th 1 per second. So seconds to the negative 1 or 1 over second. Calculate the energy in joules of the photon. So energy is energy equals Planck's constant times frequency. This is 6.63 times 10 to the negative 34th joules times seconds. Again, you'll never have to memorize this number. I'll always give it to you on a test or a quiz. So we have the frequency, nu. We have Planck's constant. We just need to find E. Okay, there's Planck's constant. And we're going to multiply by the frequency, 6.8 times 10 to the 15th, 1 over seconds. Our seconds will cancel, and all we have left over is joules. So 6.63 times 10 to the negative 34th times 6.8 times 10 to the 15th is 4.508 times 10 to the negative 18th joules, because joules is the only thing left over, and joules represents energy. All right, go ahead and try to do number 3 on your own. It says find the energy in joules of the wavelength of 650 nanometers. So you're going to have to go back and use C equals lambda nu to find out the frequency, and then you can do energy equals Planck constant times nu to figure out the energy. So take a second to work through that problem, and then I will reveal the answer. Okay, so 650 nanometers. If I use this equation, C equals lambda V, I can't use nanometers because the speed of light is in meters per second. So 650 nanometers, for every 1 nanometer, there's 1 times 10 to the negative 9th meters. So that's 6.5 times 10 to the negative 7th meters. So 3.00 times 10 to the 8th meters per second equals lambda, which is wavelength, in meters, times frequency. So now we need to find the frequency so we can later find the energy. So 3 times 10 to the 8th divided by 6.5 times 10 to the negative 7th gives you 4.62 times 10 to the 14th seconds to the negative 1, because I'm left over with this seconds here when my meters cancel out. All right, so now I can use that in this equation. So I'm going to turn my paper just a little bit to the side so that I can use it. So E equals, HV So E equals Planck's constant, 6.63 times 10 to the negative 34th joule seconds, times my new frequency, 4.62 times 10 to the 14th. Seconds to the negative 1. So now my units of seconds will cancel. Just multiply these two numbers together, and you'll get the energy in joules. So I got 3.06 times 10 to the 49th joules. Is that right? Oh no, because this is negative 34. I accidentally put positive 34. Okay, so let's try that again. 4.62 times 10 to the 14th times 6.63 times 10 to the negative 34th. There we go, negative 19th joules. That makes more sense. That would have been a lot of energy for one little photon. All right, try number 4 on your own, and then resume the video, and I will show you how to solve it. Okay, number 4 says the sodium vapor lamp emits light photons with a wavelength of 5.89 times 10 to the negative 7th meters. Oh, that's nice. They already gave it to us in meters. What is the energy of the light emitted? So to find energy, we need to use H times V, or Planck's constant times frequency. So we don't have the frequency yet, but we can get it by doing C equals lambda nu. If we have the wavelength and we know the speed of light, we can find the frequency. So C is 3 times 10 to the 8th meters per second. Lambda, they gave it to us in meters, which is perfect. 5.89 times 10 to the negative 7th meters. We're just missing frequency. So 3 times 10 to the 8th divided by 5.89 times 10 to the negative 7th to get frequency by itself. You get 5.09 times 10 to the 14th seconds to the negative 1. My meters cancel out. And that's going to be my frequency. So now E equals HV. Now I can find the energy at this frequency. So H is 6.63 times 10 to the negative 34th joule seconds. It's Planck's constant. Times the frequency, which is 5.09 times 10 to the 14th seconds to the negative 1 power. So here, my seconds will cancel, and I'm left with just joules. And so I'm just going to multiply the two. So I got 3.37 times 10 to the negative 19th joules, because joules is the only thing left over. And that's it. That's the only math that we're doing. So above that, we use this frequency and we use these wavelengths to determine the energy of different electrons. And this is how Niels Bohr found out that electrons existed in different energy levels. He took what's called a discharge tube. So it's basically like a neon light. Whatever neon lights that you see for an open or close sign is basically what he did here. And he concentrated this color and shot it through a prism. Now white light, when you shine white light through a prism, it just is this nice, beautiful, continuous rainbow. But what happens when you shine just one single element through a prism is you don't get this continuous rainbow. Instead, you get very discrete colors at very discrete wavelengths, which means these discrete wavelengths correspond to a discrete energy. So Niels Bohr said, well, if I'm getting very specific energies for each different element that I put through this discharge tube, this must correspond to a wavelength, and that wavelength meaning the electron. So these different places here pretty much show the different placements of electron could be when it's excited with an energy. So we look at what's something called an emission spectrum. An emission spectrum means all the different energies an electron can produce or give off for each element. And it's like the fingerprint of an element. Each element has a very unique emission spectrum. Sometimes you might have colors line up, like here between neon and sodium, and sometimes like hydrogen and helium, but they're never going to be exactly the same. Sometimes you'll have things in the red spectrum, but they're off just a little bit. So these always correspond to where the electrons are in an orbit, or orbital, we'll talk about later. So when you excite an electron, you're moving it from what's called the ground state, where it's naturally located, to a higher state. This is what Niels Bohr did with his emission tube. He excited it by adding some energy to this vapor of a certain element. And when he excited it, it moved to a certain energy level. So let's say this one, it moved from the first energy level to the third energy level. And then once it loses that energy, or once that energy is no longer there to keep it at the third energy level, it'll relax back down. And when it relaxes back down, it will give off the same amount of energy that it required to move energy levels. So this is a phenomenon. Not only do these guys go from one energy level to another, but they need a very specific amount of energy required to do so, and they give off a very specific energy according to where their energy levels are located. And each element is different. So when the element relaxes back to the ground state, it gives off energy in the form of a visible light. You might also see things called an absorption spectrum instead of an emission spectrum. This would happen when an electron goes from one energy level to another. Instead of getting like a black background with some colors popping up, you will get a colorful background, and then you'll get some like black lines here showing that energy has been absorbed, and there's the absence of that color because it was required for the electron to move to a different energy level. So this is why we've been studying light, and this is why we've been studying light frequency and wavelength. We will need this in order to figure out the nature of electrons and how to predict their locations and what they will do in order to form bonds and create element characteristics. So more on that to come.